Hello everyone, this is Spencer Snowling from Hydromantis. I'd like to thank everybody for coming to the next in our continuing series of webinars that we've been running over the past little while. Today's webinar is going to be about using GPSX to design and optimize upflow anaerobic sludge blankets. And I'm happy to have my friend and colleague Rajeev Goel here today to deliver that presentation.
Hello everyone.
So I'm going to start by preparing a few slides here, and I see that here at the last moment we have quite a few people joining in, so I'm just going to pause a moment where we can let a few others join us. Our plan for today, let me be able to move my slides here, there we go. My plan for today is to just have a brief introduction to Hydromantis if you have not had the chance to learn about us in the past. To have Rajeev talk about UASB modeling in GPSX, which is going to include a desktop demonstration, and talk about a few new and upcoming things that are going on here at Hydromantis these days. And also we'll leave some time at the end to take a few questions. You'll find that now that you've started enjoying the webinar that there is a questions box. You can type your questions in there and they'll come up on our screen. And when we get to the end, we will read a few of those and answer them. If we run out of time, we will respond to your questions after the webinar is over via email. So just to introduce Hydromantis, we are celebrating this year our 26th year working in the field of wastewater modeling. We are located in Hamilton, Ontario, Canada, and we were founded in 1985 by Dr. Gilles Patry out of McMaster University. So Rajeev and I are speaking to you from our head office here in downtown Hamilton. We have two areas of focus. As you all know, we produce several different kinds of environmental engineering software for the wastewater field, and we provide a number of modeling consulting services that go along with those. So you may be familiar with GPSX, the process simulation and optimization software that we'll be talking about today. What you see on the screen there is version 6, which we released at WEFTEC last fall, and it's almost WEFTEC time again, and we'll be releasing a new version, 6.1, next month. We also produce CapDetWorks for preliminary design and costing. We have a package called ToxChem that's for industrial wastewater treatment plant modeling, and we released a new version in earlier this spring. And we also have a package for doing drinking water treatment modeling as well. Okay, so I'm going to pass the microphone over here to Rajeev Goel, who's going to be talking about how to use GPSX to model UASBs.
Thank you, Spencer. So we'll get into the main topic of today, which is modeling of UASB, EGSB reactors in GPSX. And to start with, I'm going to give you a small introduction about these reactors. As most of you already know, UASB and EGSB reactors are mostly used in high-rate applications. Most of the times, you will find their applications in anaerobic treatment, but also they are being used in high-rate denitrification and also sometimes in NMOX reactors. So just to tell you the concept of UASB, EGSB reactors, they are tall reactors varying from 10 to 25 meters, having a granular sludge bed inside them, and they have a gas-solid separator at the top of the reactor. The purpose of the gas-solid separator is to separate the gas which is generated inside these reactors and then extract that gas from the top. And a clarified effluent, it also serves the purpose of solid clarification, solid recovery, and the clarified effluent is taken out from the top of the reactor. Depending on the configuration of the reactor, sometimes we have effluent recycle to increase the linear velocities inside the reactor. There are several challenges to model these reactors, and we can see to model a UASB, EGSB reactor, we need different modules. First of all, we need a reaction model to model the reactions which are going on inside these reactors. Also, we need a hydraulic model to describe the flow patterns which which goes on in this particular reactor. Also, we need a solid liquid separation model, which is to model the top part of the reactor. Also, we need gas liquid separation model, which is to kind of separate the gas which are produced inside the reactors. Also, to model the solids which are coming out from the reactors and their interrelationship with the sludge blanket height, we need a sludge fluidization model. And finally, since these are the granules, we need a kind of a substrate transport model to model the biofilm reactions going on. So if we look at all of these modules and try to develop a model, it's very complex model. It's going to be a very complex model. So I'm going to just show you how we can model a UASB EGSB reactor in GPSX, and what are the assumptions which we need to make, and how can we do it in a very practical sense. So in GPSX, we can take two approaches. One is a simple approach in which we are going to use an anaerobic digester object and a solid liquid separator, from which we can separate the solids and bring them back to the anaerobic digester. In a second approach, which we are trying to develop now and should be available to everyone in the next version of GPSX, we are trying to develop a dedicated UASB object with a UASB model inside that particular object. So this particular thing is going to be made available to everyone in the next release of the software. So in a simple approach, the concept we are going to look into is the reactor, the UASB reactor looks something like this. It has a biological reaction part, a compartment, and at the top it has a clarifier object. So what we can do in a simple approach is to use a digester object and a solid liquid separator object and separate the sludge and bring the sludge back to the reactor. In this particular way, we are trying to just mimic what goes on in this particular reactor through two different objects in GPSX. In this simple approach, you can see that we are kind of accounting for the reaction model. We can also account for the hydraulic model, which is a CSTR model. Solid liquid separation model, which can either be a dewatering object or a clarifier object. Also, we are accounting for gas liquid separation model. So these four modules can be accounted for in this particular approach. But as you can see, we don't have a fluidization model and the biofilm kinetics model in this reactor, in this approach. In the next approach, which is a more advanced approach, which we are trying to develop at this particular time, is to have a dedicated unit process for modeling UASB processes. And what we're trying to do is have a built-in solid liquid separator in this particular object and a batch fluidization model. So now I'm going to give you a desktop demonstration of both of these approaches so that you can have a feel how to model these UASB EGSB reactors inside GPSX. So we have made a pre-configured layout just to save time. And in this layout, what we have done is we have an influent object in which, in the influent characterization thing, we have inputted the values for BOD, COD, TK, and TP for food processing wastewater. So as you can notice, this wastewater has a high BOD of 1500, a TK value of 100, and TP value of 50. And if we look at the total COD value, which is going through this inlet to the reactor, is 2,307. And we can characterize this as a medium strength waste. So you can input all your values here, and we have already done that for in this particular example. Also, we have a pH NaOH dosing object here, in which we are trying to feed NaOH to control the pH in this digester. So the flow rate of this chemical is 3 meter cube per day, and it goes into the combiner, and the combined feed goes into the digester. The only changes which have been made in the digester object are the volume of the reactor, and the headspace volume is 20 meter cube. And if you look at the gas liquid transfer constant, we have changed the value to 100 per day. EGSB reactors have a short retention time, and they experience a lot of turbulence inside this. That's the reason this value has to be higher for the CH4 and the CO2 which are produced in the reactor to get into the gas phase. So that's why we have increased the value of this one here. We have a solid liquid separator object, and in this object, the only setting which we have done is in the operational. We have defined a solid removal efficiency of 0.98 and a pump flow of 100 meter cube per day. So a pump flow of 100 meter cube per day is going back into the digester, and the removal efficiency is going to be 0.98. Also, you can see a controller object here, and we are going to use this one to control the amylases concentration in the digester by controlling the separation efficiency in the dewatering object. So this is the very simple layout which we can use to mimic the UASB process in a simplified way. So I'm going to run some simulations and describe, show you what kind of outputs we can expect and what we can do with this kind of simulation. So I'll go to the simulation mode here, and you can see that we have different output windows set up here and different control windows set up here. So I'm just going to run with the default settings, and I'm going to just run a steady state simulation, and you can see that the model converges, and we can see the flow rate which is going into the digester object is 2400 meter cube per day with a TSS concentration of 108 and total BOD of 1500 going into the reactor. If we look into the reactor, which is this reactor here, you can see the TSS concentration which are built into the reactor are in the range of 19,000 milligram per liter. You can also see that the gas production rate, the total gas production rate is 1,642 meter cube per day for this particular configuration with a methane content of 85%. If we look at the effluent characteristics, we can see that the TSS concentration which are going out into the effluent are 378, VSS concentration of 303, and BOD of 247. So now this is a typical input which you can, typical output which we can expect from this kind of analysis. Now, what else can we do while we are in a designing stage? Sometimes we need to, like in this particular case, we know that our TSS concentration is 19,000. But when we are designing, sometimes we want to control the TSS concentration in this reactor. So we are going to use this controller and use this controller to control the concentration of TSS in the digester. So I'm going to turn the controller on, and I'm going to run the simulation one more time, and we are going to see what difference does it make to the effluent quality, to the gas production, to the gas production rate. I'm going to run this simulation. Our gas production rate right now is 16.18. So when I run this simulation with the amylases, to achieve amylases concentration of 25,000 in this reactor, I can see the concentration in the reactor going up to 24,843, and our gas production increases to 1685 from 1640. So there is a slight increase, or almost 2 to 3% increase in the gas production if we increase the concentration in the reactor to 25,000. Also, sometimes we want to see, we want to do certain analysis in which we want to see what is the effect of digester size or the UASB reactor size onto the performance of the reactor. So what I've done here is we're going to turn off the controller and reset the model and try to run an analysis in which we are going to change the reactor volume. So I'm going to change the reactor volume from 300 to 500, and we're going to see how it affects our gas production rate. So we're going to go to the analyze mode. So as soon as we go to the analyze mode, you can see this changes from 200 to 400, which is the reactor size I'm going to analyze. And we are going to see that if we run the steady state simulations, the reactor size are going to change, and at each reactor size, we are going to see what is the CH4 production rate. So I'm going to run this analysis. So you can see that when we change the size from 200 to 400, the gas production rate changes from 1270 to 1464. And if you keep on increasing the reactor size, at a certain stage, there will be a stage when there won't be a significant increase. Like at from 360 to 400, already the curve has started to kind of flatten off. So this kind of analysis are pretty easy, and you can do that in GPSX to figure out, to see the effect of reactor size on the effluent quality, and use this information for designing. So this is something you can do very easily, and this you can do if you have GPSX version 6. And but if you have versions which are the earlier versions, then you won't be able to do this analysis. So this is only you can do with Mantis 2 Live, which is available in version 6. So now I'm going to go to the next approach, the second approach, which will show you what we are trying to develop for the next version. So in this particular approach, what we have tried to do is it's the same layout, but as you can see in this particular layout, we have changed the anaerobic digester and the sludge return object with a single object, which we are calling EGSB Reactors. So this is a new icon, or the new unit process which will be available in the next version. Just to show you that we have the same influent characteristics here for this particular layout. Also, we are feeding the same amount of NaOH to the reactor. And I'm going to just show you what kind of simulations we can expect from this unit process model. So go to the simulation mode, and you can notice that I'm going to run a dynamic simulation for this particular case scenario, for this particular case. And it is 1 day of simulation in which we are going to change the influent flow rate and see the effect on the sludge blanket height in the EGSB reactor. So if I just run the simulation, it goes to the steady state, and it's running at a constant flow rate, and we increase the flow rate into the reactor to about 1.5 Q and bring it back after a certain stage. So you can see the effect of this particular change in the influent flow rate. You can see it on the sludge blanket height. You can see the sludge blanket height in the reactor increases, and when we decrease the flow rate, it comes back to the normal position. This particular line shows the sludge mass in the reactor. You can see we started with a certain sludge mass, but as soon as we increase the flow rate, there is a loss of solids, and we lose quite a bit of solids, which brings down the mass of the reactor in the mass of the solids in the reactor. If we look at the gas flow and the methane fraction, since we increase the flow rate, we are bringing in more COD to the reactor. We can expect an increase in the gas production rate, which we do here. At the same time, when we are bringing in more substrate, but we are not adding enough alkali solution, the pH of the reactor goes down and there is more CO2 coming out from the reactor, which brings down the fraction of methane a little bit lower than what it was before. And also we can see what happens to the effluent quality. So the black thing here shows the suspended solid concentration. As soon as the flow increases, there is a slight increase in the effluent solid concentrations. But as the solid blanket height crosses a certain level, there is a significant loss of solid. When we reduce the flow rate, the solid loss from the reactor goes down and comes back to the level which it was before. So we have tested the model, and we have seen the behavior of the model, and the general behavior of the model is according to the expectations, and we are doing further testing with this particular model, and hopefully we'll be able to release it in the next version of 6.1. Just to give you some information what additional parameters we need, or what additional parameters you can get out of this model is, if we go to sludge bed, the model estimates the terminal velocity of the granules, based on which the fluidization of the bed is estimated. You can also get the value of the volume of the stationary bed and the superficial velocity in the reactor. Also, you can see there is a volume of the sludge bed, which is the expanded bed. So if we compare the volume of the stationary bed with the sludge bed, you can see there is some expansion going on here. Also, the solid concentration in the bed is estimated. Just to let you know what parameters do we need, additional parameters do we need to set up this model. If we go to this particular object and click on the parameter for bed fluidization, we need the information on the average granule size for this model to work. Also, we need some variables or the parameter values which are required to estimate the sludge blanket height in the reactor. Also, we need some information about the GSS parameters, like what is the solid capture rate or solid recovery efficiency of the gas-solid separator for the reactor. So we need all these parameters to set up this model. And now I hope this gives you a little bit of information about the simple way of doing EGSB in GPSX, and also what's coming up next. So I'll go back to my slides, and just to do some conclusions. With a simple approach, we can do quite a lot of things at a designing stage. We can see the effect of reactor size on the effluent quality. We can also look at the gas production rate and the methane content, solid production rate, and also we can look at the alkalinity requirement. If we want to maintain some specific pH in the reactor, we can look at all those aspects of the UASB reactor. In the advanced approach, the advantage is you have one unit process which handles all the things with a built-in solid liquid separator, and it has a fluidization model. So it kind of gives you additional information about the sludge bed dynamics, like how it is affected with the flow rates and other things. And this kind of information gives you useful insights into the operation of this reactor. As I said before, we are expecting this unit process to be available in version 6.1. And with this, my presentation is over, and I'll give it to Spencer to talk about something, what's new in Hydromantis.
Thank you, Rajeev. I'm just going to take a few minutes here to just highlight a few things that are going on at Hydromantis right now. As you may know, we released a new version of ToxChem, our package for modeling the fate of organic compounds personal care products and metals and any other kind of micro-constituents in a wastewater treatment plant. This is a very substantial update to the software that's used quite a bit in the industrial industry. So we have another upcoming webinar on that shortly. We have expanded our video library at our website so that you now have full tutorial videos on how to use GPSX, ToxChem, and CAP.Works, so they're free for you to access and take advantage of as you need them. We continue to offer our web-based training packages, so if you are a user of GPSX or any of our software and you would like to arrange for a remote web-based training session for your company, please give us a call. So our next webcast is Wednesday, October the 12th at 2 p.m. in the afternoon, and we are going to be covering how to use ToxChem version 4.0. So this is a repeat of an earlier webinar. If you haven't had a chance to take a look at ToxChem, then we invite you to pop over to our website, go to the webinars tab, and you can register for the next webcast. I'd also like to highlight that we will be at the WEFTech conference that's coming up the week of the 16th of October. And we are there, as we usually are, with a number of presentations, and we also have a booth that we would like you to visit. We are located in the main hall, and we are at, I'm sorry, the booth number skipped by there. We're located towards the back there, and I'm sorry, I've lost the booth number off of this slide, but I will let you know in a follow-up email. So lastly, we continue to offer the expert modeling services that we provide for our software. We can help you put together a model for you, help you with the calibration of it if that's required. We have some expertise in designing sampling programs for the purposes of collecting data for model calibration. And we also offer a full suite of modeling consulting services. If you have a plant and you would like to carry out a modeling study, we can be brought in to do that for you. So at this point, we would like to thank you for attending, and we have several minutes available now to be able to answer any questions that you might have about today's presentation. So to be able to do that, you can open up your in your webinar dashboard there the questions box and type in a question, and I will start going through those, and Rajeev will be here to answer them. So the first question we have today is what is the purpose of the toolbox object in the simple version?
The toolbox object is used to control the MLSS concentration, the solid concentration in the digester in the simple layout. So what I did basically was to set the control variable to the MLSS in the digester, and the manipulated variable is the variable is the recovery solid recovery factor in the dewatering object. So when I put the controller on, it automatically estimates what should be the solid recovery factor to achieve the MLSS concentration of 25,000. So that's what I showed in one of the simulations, and that was done through the toolbox object.
Okay, so thanks, and we have another two-part question here. The first part is, can you please comment on the fact that absorption mechanisms are not yet available in the current model in version 6, whereas in very low retention time / high TSS concentration, these mechanisms might be important contributors to BOD removal. So how far are we making mistakes by neglecting this?
Well, in version 6, actually, if you look at the Mantis 2 library, I think we have included the absorption mechanism. We have the colloidal COD in Mantis 2, and we consider absorption of this one onto the solids, and this is included, I think. I'm not sure whether this is what you mean, but if you are looking at the absorption of colloidal COD onto the biomass, then this particular mechanism is built into Mantis 2 library. But it's not there in other models which have been published by IWA, like ASM2D and ASM1. But we have included this particular mechanism in Mantis 2 library. And the second question is,
are you planning to apply a module to include biological reactions in activated sludge clarifiers? Essentially, the answer to that is that we already have biological reactions in our clarifier models. It depends on which model that you have selected. So the short version to that is you can either have it, the biological reactions, either turned on or turned off depending on the selection of your model. So if I just grab one of my clarifiers here, you'll notice that when you select the model, if you select simple 1D, that is our default model selection, you are selecting a non-reactive model. And if you select any of these other ones, such as ASM1 or Mantis, then you are selecting the version that does the settling and the biological reactions together at the same time. Okay, well, I think we have time maybe for one more question here. Let's see. Enter this one here maybe. Okay, so we have another question that says, does the biological reaction model for UASBs and EGSBs include the primary stage of hydrogen production before methane production?
Yes, in the Mantis 2 lib, actually, the process of in the anaerobic reaction scheme, actually we produce hydrogen. So there is a step in which hydrogen is produced. Maybe we can show the process here. I'll just show you how it works. So if you go to the kinetics here, and just for the previous question, actually we have the absorption of colloidal COD here in this particular model. And to come back to the question of hydrogen, we have hydrogen producing biomass in this particular, in the fermentative stage, actually we produce hydrogen, and from hydrogen, hydrogen then can be combined with CO2, and there are hydrogenotrophic methanogenic biomass which uses the hydrogen and produces methane. So this is a simple scheme, like in a fermentative reaction we produce hydrogen, but I'm not sure whether you are thinking for more elaborate scheme of hydrogen production. So we have one single step in which hydrogen is produced, and then it is consumed by hydrogen utilizing methanogenic biomass, and that's the scheme we have got in this particular model. Is that okay?
Okay, I think that's it. We've used up our 30 minutes here, and I thank everybody for coming out. I see here that we have a number of questions that are still outstanding. So what we're going to do is we will respond to you individually with an answer to your question in a follow-up email. So if you have any further questions about the information that we've shown today, or indeed any of our products or services, we invite you to write to us. We had our contact information here on the previous slide, and so we look forward to hearing from you. You'll receive a follow-up email from us with a special offer for licenses for webinar attendees. And we look forward to seeing you, hopefully in the near future, at WebTech or some other conference. And as always, we look forward to hearing from you by email if you can't see us there. Thank you very much. And again, I thank everybody for coming out today.
Thank you.